Equivalence relations. Hello everyone. To begin, let's take a moment to look back at what we have already covered. In our previous subsections, we explored three fundamental properties that a relation can possess: reflexivity, symmetry, and transitivity. Now, while each of these properties is important and useful on its own, they become exceptionally powerful when they occur simultaneously within a single relation. This leads us to our core topic for today. When a single relation possesses all three of these characteristics, meaning it is reflexive, symmetric, and transitive, it is known as an equivalence relation. In the upcoming slides, we will dive deeper into the formal definition and learn exactly how to verify if a relation fits this criteria. Definition. Now that we have introduced the three fundamental properties, let's move on to the formal definition. A relation, which we will call R, defined on a set A, is known as an equivalence relation if and only if it satisfies three specific conditions. First, the relation must be reflexive. This means that for every single element, A belonging to set A, the pair A, must be an element of the relation R. In other words, every element must be related to itself. Second, the relation must be symmetric. This means that for any two elements A and B in set A, if the pair A, B is in the relation R, then the reverse pair B, A must also be in the relation R. Third, the relation must be transitive. For any three elements A, B, and C in set A, if the pair A, B is in the relation R, and the pair B, C is also in the relation R, then the pair A, C must necessarily be in the relation R as well. It is crucial to understand that these three properties are a package deal. If any one of these three conditions fails to hold, the relation is not an equivalence relation. Now that we have the definition clearly established, we will proceed to the next slide to discuss the systematic steps you should follow to verify these properties in a problem. How to verify an equivalence relation. Now that we have defined what an equivalence relation is, let's look at how we actually prove it. To determine if a given relation R on a set A is an equivalence relation, you should follow these three systematic steps. First, we perform the test for reflexivity. Here, you need to check if every single element in set A is related to itself. In mathematical terms, you are asking, does the pair A, belong to the relation R for every element in set A? If even one element is not related to itself, the relation cannot be an equivalence relation. Next, we move to step 2, the test for symmetry. To do this, start by assuming that a pair A, B exists in relation R. Now, you must check if the reverse pair, B, A, must also exist in relation R. Essentially, if A is related to B, then B must also be related to A. Finally, we have step 3, the test for transitivity. This one is slightly more complex. Assume that two pairs exist in relation R. The first pair is A, B, and the second pair is B, C. You then need to verify if the resulting pair, A, C, must also exist in relation R. In other words, if A is related to B and B is related to C, then A must be related to C. To conclude, if all three of these steps are verified as true, then you can confidently state that relation R is an equivalence relation. If any one of these tests fails, the relation does not qualify. We will see how to apply this process in a real-world example in the next slide. Real-world example, parallel lines. Now that we have discussed the theoretical steps for verification, let us apply them to a practical, real-world example using geometry. First, let us define our environment. Consider a set, which we will call L, consisting of all possible lines in a two-dimensional plane. Within this set, we define a relation, R, where line L1 is related to line L2 if, and only if, line L1 is parallel to line L2. To determine if this is an equivalence relation, we must follow the three-step process we established in the previous slide. Step 1 is checking for reflexivity. We must ask, is every line parallel to itself? Yes, by definition, any line L1 is parallel to itself. Therefore, the pair L1 belongs to the relation R for all lines in set L. Consequently, the relation is reflexive. Next, we move to step 2, checking for symmetry. Let us assume that line L1 is parallel to line L2, which means the pair L2 is in our relation. If this is true, it is logically certain that line L2 must also be parallel to line L1, meaning the pair L1 is also in the relation. Thus, the relation is symmetric. Finally, we proceed to step 3, checking for transitivity. Suppose we have a scenario where line L1 is parallel to line L2, and line L2 is parallel to line L3. According to the fundamental properties of geometry, if two lines are both parallel to a third line, they must be parallel to each other. This implies that line L1 is parallel to line L3, meaning the pair L3 belongs to the relation. Therefore, the relation is transitive. In conclusion, because the relation is parallel to, has been proven to be reflexive, symmetric, and transitive, it satisfies all the necessary conditions to be classified as an equivalence relation. Now that we have seen a successful verification, let us move forward to discuss some common mistakes students often make during this process. Common mistakes to avoid. Now that we have seen how to systematically verify an equivalence relation using the example of parallel lines, it is important to discuss some common pitfalls. Let's look at the common mistakes to avoid. First, let's discuss the 2 out of 3 error. A frequent mistake students make is assuming that if a relation is already reflexive and symmetric, it is automatically an equivalence relation. Please remember that for a relation to earn this title, all 3 properties, reflexivity, symmetry, and transitivity, must be proven independently. You cannot assume the third property is true just because the first 2 are. Next, be careful about ignoring the domain. You must always check the set, which we refer to as set A, on which the relation is defined. This is critical because a relation might satisfy all the conditions on one specific set, but fail to be an equivalence relation if the set is changed. Third, there is the issue of misinterpreting transitivity. Many students struggle with the if part of the transitive property. It is important to understand that if you cannot find any pairs, B and B, C in the relation to begin with, the condition for transitivity is what we call vacuously true. This means the property has not been violated, so it is still considered transitive. Do not mistake a lack of pairs for a failure of the property. Finally, avoid confusing symmetry with reflexivity. While they may seem similar, they are distinct. Symmetry involves the relationship between 2 elements, where if A is related to B, then B must be related to A. Reflexivity, on the other hand, is a specific requirement that every single element in the set must be related to itself. By keeping these warnings in mind, you will be much more precise in your proofs. Now, let's move to the final slide to summarize our key takeaways. Key takeaways. To wrap everything up, let's go through the key takeaways from this lesson to ensure you have a solid grasp of the concept. First, as we have discussed throughout the presentation, an equivalence relation is a relation that is simultaneously reflexive, symmetric, and transitive. Remember, as we noted in our common mistakes slide, you cannot skip any of these. All 3 must be present for the relation to qualify. To recap the mathematical requirements. Reflexivity means that for every element, A in the set, the pair, A, must belong to the relation R in simple terms. Every element must be related to itself. Symmetry means that if the pair A, B is in the relation R, then the pair B, A must also be in the relation R. This is the two-way street property we saw in our parallel lines example. And transitivity means that if the pair A, B and the pair B, C are both in the relation R, then the pair A, C must also be in the relation R. This ensures a consistent chain of relationship across the set. Finally, it is important to understand the purpose of these relations. Equivalence relations are used to group elements of a set that share a common property. By doing this, we can effectively treat these different elements as equivalent within a specific context, which simplifies complex mathematical structures into manageable groups.